Hey guys, so today we're going to be going over the Lab 2 magnetic field of a bar magnet. So in this lab, we essentially measured how the magnetic field of a bar magnet changes with the distance that the magnet is, uh, and then we modeled the magnet as a dipole. The experimental value we reached was N is approximately -3.0054, and this closely matches the theoretical prediction of N equals -3, showing strong agreement with our model. Using the same data, we also calculated the magnetic dipole moment to be approximately 3.61 A times m squared. So the fundamental principles, the main physics principles in this lab that we used to model the magnetic dipole. Basically, we described how a bar magnet produces a magnetic field in space, and to analyze this field and how it changes with distance, we use relationships like B is equal to KR to the N, where N describes how quickly the field decreases. And then by plotting natural log of B versus the natural log of R, the slope value gives us an estimated N, which is expected to be around -3 for an ideal magnetic dipole. So experimental procedures. We aligned the phone with magnetic north and then placed the bar magnet along the east-west axis and located a magnetometer chip. We then measured the distance between the magnet and the sensor while recording the B values. The average measure was then used to create the natural log of Bx versus the natural log of R, and then the graph was used to analyze how the magnetic field changed with distance. So this is our data and analysis on the axis. So for on axis, we use the average distance and B values to create a natural log B versus a natural log R graph. The trendline equation y is equal to -3.0054x minus 14.49 gave an experimental value of n is equal to -3.0054, which closely matches to the theoretical dipole value -3. Using the y-intercept, we can also calculate the magnetic dipole moment to be approximately 3.61 am squared. So this is the calculations. Sorry. So for the calculations, we use the power law model of B, or the magnitude of B, is equal to KR to the N, and converted it to a linear form where natural log absolute value of B, or magnitude, is equal to natural log of K plus N natural log of R. The trend line from the N B versus the NR graph gives us N is equal to -3.005. And that matches, again, the theoretical dipole value of -3. With the y-intercept, we found that K is equal to 7.16 times 10 to the -7, and can estimate the dipole moment to be approximately 3.1 or 3.61. So this is the data analysis we got off the axis. For off-axis analysis, we measured the magnetic field at a 45-degree angle from the magnet's axis, where the field contains multiple vector components. This requires calculating the total magnetic field and using geometry to determine the distance between the magnet and the magnetometer chip. Because of additional uncertainties from Earth's magnetic field and spreadsheet correction errors, the off data was mainly used as a comparison to the on data measurements. This is the code for our computation model, and this is initial conditions set. So for the computational model, we defined mu naught over 4 pi is equal to 1 times 10 to the -7, placed the bar magnet at the origin, and assigned it a magnetic dipole moment of 3.61 A times m squared directed along the positive x-axis. We then created a dipole moment, B mu r function, to calculate the magnetic field at any observed point. This allowed the magnetic field to be visualized for on-axis, off-axis, and 45-degree positions. So this is the visual component of our code. In this part of the computational model, we visualize the magnetic field at a 45-degree observation point defined as observation underscore 45 degrees, where the vector is equal to d perpendicular, and 0. The dipole B function calculated the magnetic field vector and displayed an arrow showing its direction and relative magnitude. The results showed that the field at a 45-degree position has both x and y components rather than pointing in a singular direction. So our assumption and errors: for this lab, we assume that the bar magnet behaves as an ideal magnetic dipole, and that the magnetic field follows a power law relationship with distance. Major sources of error include interference from nearby magnetic or electronic objects, and uncertainty in locating exact positions of phone's magnetometer sensor. Because the magnetic field has an approximately as 1 over r to the third power, even small distance errors could significantly affect the results. Observations. In the observation portion of the experiment, the measured Bx value was very small when the magnetometer was far from the bar magnet and increased as it moves closer. The largest field values were recorded at the shortest distances, showing that the magnetic field decreases as distance increases. So they're, inversely proportional to one another. The observations support choices 1 and 4, since the field was weak far away and stronger near the magnet. Again, they are inversely proportional to one another. Distance is inversely proportional to strength. Discussion. If the magnetic north had not been correct for Earth, Earth's magnetic field would have altered the measured Bx values and reduced the accuracy of the results. This could have caused the experimental value of N to differ from expected -3. Continuing two identical magnets end to end would approximately double the dipole moment of 3.61 A times m squared to approximately 7.22 A times m squared, producing a stronger magnetic field while maintaining the same overall field pattern. And that is all we are coming to discuss today. I hope you have a great day.